Now I'll demonstrate how you build an instantaneous cause and effect relationship where you use a graph function. And let's start by placing this exogenous variable, and in this case it's the spawning stock of a fish, and that will influence the recruitment of fish. And we link the two variables like that. We can move around to make it look nice. And now the spawning stock. In this case I'll demonstrate another input than the step input. I'll demonstrate the ramp input. So I choose ramp, and you see it's a built-in function. And then if I right click here, I get a choice to see the definition of ramp. And it says the first parameter is slope, that's how fast it increases. And the second one is time, at what point in time it should start increasing. So let's choose a slope of 0.5, and then it starts after 2 time units. In this case it will be years. So there we have defined the spawning stock. And well, we need a unit here as well. And let's choose a unit of million tons. And then and then we have to describe how recruitment depends on the spawning stock. And first we see here that spawning stock is the input variable, so we choose that. And then we choose a unit, and in this case we choose billion in the American sense, billion or not individuals, let's say billion fish. So that looks a bit strange now that spawning stock suddenly has the unit of fish, but the unit here has to do with the graph function. So we choose the graph function, and then we set well, first we have to click here, graphical function, and then I choose a scale here of 5, and the input, the spawning stock, can go from 0 to 10 million tons. The number of points, well, the suggestion here is 11 points, and we can choose that. And now I can just draw, by clicking in the diagram, I can draw the relationship just as I want. Let's see, fine-tune a little bit here and there. Just click on it and drag it. And then always when you drag a function like that, it's a good idea to go and check the points where you know exactly what it should be like. And in this case, we know that when the spawning stock is 0, then the recruitment should be 0. So go in there and enter 0 and click return, and then we go back to the graph. Well, then maybe we should reduce it a little bit, but of course we don't know exactly what this is. This should be based on data as shown in the reading material. So there we have that. We can go back to the equation part, and we see it's billion fish, and there is no warning that the unit is wrong. Well, we can also go in here and check the units, check units, and units of measure are consistent with the equation. So that's fine. So now we have our model. Before simulating, we need to set the time scale. And in this case, it's more natural to say that we run in years. And say we run for a 20-year period. Choose a shorter dt. So that should be it. And then we choose the graph tool. We click command and draw in the spawning stock, and then I can click here and enter manually the recruitment. So I click plus, and then I can choose recruitment. So there we have both of those variables. We could also go in here and define, say, the minimum y value is 0. and you can define a maximum value as well, like that, and then we simulate. First, notice that the spawning stock follows the ramp function. It increases after 2 years, and then the slope is 0.5 units per year. So this is how the spawning stock develops. And then you see that recruitment, as long as the spawning stock is 0, there is no recruitment. And then as the spawning stock increases, we get first a rapid increase in recruitment, and then it tapers off and saturates because of the nonlinear function that we chose. So this graph shows the development over time. So let's go back to the edit mode, and then I can move this a little bit up, and then I want to see if we can get an indication of the graph relationship, the nonlinear relationship. So I open a new graph, and then I choose scatter, and then I first add here the spawning stock, which is on the horizontal axis, and then series 2 is the recruitment. And there you see, since I already simulated, you already have the data, and when we use the scatter plot, we see the data points will then follow this nonlinear relationship. So the relationship that was in recruitment can be demonstrated by using the scatter plot. To make the graph look a little nicer, I can click on recruitment, and then I choose a smaller thickness. So I minimize that, and this now looks like a solid curve. But if we go in here and choose a longer time step and run it, then you see that this curve consists of data points. It's a scatter plot. Finally, I'll show you how to build an accumulating cause and effect relationship. The center of an accumulating stock and flow relationship is the stock. So I go up here, choose a stock, place it in the diagram, and let's say this is the amount of fish. And the one thing that you need to do here is to set the initial value. It's like a container, it's a stock, and then it needs an initial value. So let's choose here, say 4, and that could be measured in billion fish. And then we know that the stock is only changing through flows. So I choose the flow symbol, and then I place that somewhere in the diagram and click and draw it into the stock, and there it connects. And then we have an outflow. I click on the same symbol for flow, click inside the stock and drag it out, and there we have an outflow. And you see now that the solid arrow is pointing in the direction that the flow is going here by definition. So then let's give names to the flows. So let's call this recruitment, and the outflow is deaths. And then I click on that, and the circle that you see here it's just like any other converter. Same way to define it. So in this case, let's just assume that it is 4. And you see here that it already gets a unit, because it must be billion fish, because the flow is flowing into the stock of fish. So it must be billion fish. And it is per year, because we have defined the time scale to be years. So it's automatic. Once you have the right unit for fish, the flows will also be correct. So that was 4, and then let's double click on that and say that that's 2, and again billion fish per year. And that's it. And now we can look at how this develops over time. So we choose again the graph symbol, we draw in the fish stock, and well, we can have another graph for the in and outflow, recruitment, and deaths. And then we simulate. And here you see that recruitment is all the time higher than deaths. And because more is flowing in than out, we see that the fish stock is increased, and it's increasing linearly along a straight line. So then, when you go on building models, you can combine instantaneous cause and effect relationships and accumulating cause and effect relationships. Good luck.